Today is going to be a pretty mellow class because we are just going to start talking a little bit about the organization of our galaxy, which will prepare us to think about galaxies in general and how they form. And of course, we are getting pretty close to building out that story of the cosmos itself. This is kind of the last puzzle piece, I think, in terms of the individual objects that we're going to be talking about. So, good news is there's far less controversy in today's subject matter than maybe everything else we've talked about. Of course, we know perhaps the least about, the further we get away from our own solar system, the less we understand. And getting into galaxies, especially other galaxies, trillions of kilometers away, is going to become very difficult to parse. So before we get there, why don't you all tell me what some holes were in what we talked about last time? Where did you all get lost? What's interesting? All right, good. Some enthusiasm. Yeah.
So we talked a little bit about how the radius of stars eventually collapse because they're cores are burning. And you said that eventually they'll collapse so much that their radius reaches zero.
That is the standard gaseous model. Yes.
What does a star with zero radius but still is existing?
Yeah, that's a totally reasonable question. I asked that question when I was about 11 years old. I kind of was a super nerd as a kid, and I was really interested in these questions, which has led me to standing in front of you guys today. Which actually led me to the liquid model of stars eventually. Yeah, it does kind of stretch the imagination. What does that mean? I tried really hard to present to you guys exactly, and I think it's probably worth reviewing too, how in the world we came about that idea in the first place. Why do we think that? And so there's two kind of prongs to it to understand how modern astrophysics arrived at that conclusion. One is a very mathematical approach, which involves understanding how people came up with the idea that, let's say, how people came across the idea that if you extend the relativistic equations to their limit and you cram enough stuff into some place in those equations, that you essentially reach a point at which there's essentially an unending amount of gravity, right? This is called a singularity, right? It's also so large that, of course, it collapses all matter into itself. That's kind of the physical result of pursuing those equations beyond perhaps their physical reasonableness. And so I tried to bring up this idea to you guys last time about boundary conditions. I didn't have a killer example of it, and I probably should. I'm going to go back to the workshop and think of that for you. But in almost every other science, when you fit a curve to something, you need to specify the boundary conditions upon which your curve will fit the data, basically. You don't really extend those parameters beyond that. So that's the mathematical angle. The other angle is perhaps the deep need to understand the mystery at the heart of why some stars seem to orbit stuff that we can't see, which is really a reasonable mystery. It's a pretty, I don't want to use the word problem, but it's a kind of a big problem. Why do we, generally speaking, we see stars orbiting each other? It makes sense for the most part based on, what we read as their mass by their luminosity relationship. But what happens when stars are orbiting dark stuff? What the heck does that mean? And so, a very convenient solution to that in the wake of the popularity of relativity is that it is one of those singularities where physics itself stops working, where the equations kind of break down. And so this is how we get the black hole over the course of many generations of mathematicians and observationalists being puzzled by these points. So does that make sense? What do you think, guys? I know the idea is quite attractive too. It is, I think that the more that we expect physics to provide the story of everything for us, the more that we want to expect that there's something more to it than just atoms crashing into each other or pulling on each other. But I'm not sure that physics is really the right way to go about explaining everything in the universe to ourselves either. It's a very interesting puzzle. I don't know. Did that answer your question in any way, shape, or form? What else sticks out to you at this point? It's a hard question to answer. Yeah, what does it mean to have zero volume? I mean, I've tried really hard to approach these kind of problems as charitably as possible. And it's hard for me to understand how such an idea is considered science, to be honest with you. But at the same time, I can understand how it happened, too. It's harder for me, perhaps, to understand the appeal of it. But I think you have to understand that the great majority of cosmologists are mathematicians. They're not observationalists at all. They're definitely not people who do experiments in laboratories. And from a mathematical perspective, that's perhaps a reasonable conclusion of fitting those curves and following them to their infinitesimal conclusions. I don't know. What do you guys think? Why do people love black holes so much? You guys probably love black holes. You tell me. Yeah, Jasmine. Yeah.
Because, like, yes, we know that it like absorbs the matter around it.
Mm-hmm.
It leads up to like science fiction and all that, to the possibility of like, oh, what if it's secretly like a pathway to a different galaxy or to a future, or like something creative as that, or
100%. Yeah. I get it. I think it's super fun science fiction too. You know, you guys heard of wormholes. I don't know if they make it into your textbook at all. These wormhole things that you kind of mentioned, like a pathway to another galaxy, right? If these black holes could link up to each other. I think that was like at the core of Interstellar, the movie. Did you guys see that one? Super cool stuff. What's kind of funny about wormholes is actually, did any of you guys read the book or watch the movie Contact? It's a little bit older, maybe too old for most of you guys. So actually, anybody know who Carl Sagan is? A little bit, the OG. So Carl Sagan was a pretty awesome dude, actually. And he's got a great old, PBS Nova series called Cosmos. If you guys ever want to geek out on some old science TV, it is a fantastic series. And anyways, Sagan was kind of the original, he's kind of like Eddington, actually. He was a legitimate scientist himself, but also a popularizer of science. And he had just this kind of magical way of talking about things. And anyways, he was also a novelist. And he was writing this novel, and he needed a way for the main character to be able to go back in time, I believe it was. Or at least to reach a faraway galaxy. I can't remember, I haven't seen the movie in a long time. At any rate, he needed to basically break physics for some plot crux of his novel, which ended up being made into a movie. And so he called up his buddy who was working on Schwarzschild solutions, black holes, and so forth. I believe he was at Caltech, don't hold me to that, but his name was Kip Thorne. And he asked Kip if there was a way that the mathematics could be interpreted such that he could do this thing where he could link these black holes up to each other. And so Kip developed the idea of the wormhole to go with Sagan's novel, right? And so only in the subsequent years did people start to actually take it seriously, and then, you know, now it's kind of blurring the line between fact and fiction. But that one actually started off as a fiction, which is kind of interesting. And I actually think science fiction's probably done more for popularizing the black hole than any scientist could ever do. So there's some interesting legacy with all of that. Anyways, I think that when you expect the physicists to give you a cosmology, I think people are going to expect more than physics out of it. And I think that might be some of the metaphysical weight underneath the popularity of these ideas. Because, of course, yeah, it does completely strain the imagination as to how you have anything with zero volume, first of all. And then also there's an interesting supposition buried in there too, which is in some sense against the basic principles of science, you know, the basic principles of universality of physics, which is kind of like physics holds true. You know, the laws that we derive for nature hold true no matter what. And so the idea that physics itself kind of breaks sometimes is a very strange conclusion to reach. I don't know. What do you guys think? Anybody? Thoughts? Michael, yeah.
Like the volume of the compressed black hole would be more like a calculus function, like a limit approaching zero, but never quite gets there, because if it was zero, then there would be nothing to create gravity.
Yeah, so there are some physicists working on the black hole phenomena who don't subscribe to the singularity thing. So the singularity is the point at which everything blows apart. It's the infinitesimal point in everything. So there are physicists, including one of the guys who actually did some of the very, very early work on black holes originally. I actually pulled this article up. So this guy, Roy Kerr, way back in 1963, he came up he did a bunch of the math surrounding moving black holes, I guess it was. And he's kind of walked back on this idea in recent years, which is kind of interesting. So I think he's still trying to treat it as some sort of exotic form of compact material of some sort, but he's not completely convinced, or he's not at all convinced anymore that this singularity thing is real. And of course, all the quantum physicists are dying to come up with a quantum theory of gravity, because and in those quantum theories of gravity, there should be no singularities possible. So I think that regardless of what happens next with the black hole, I think the singularity idea is losing some steam for sure. So yeah, it's an interesting situation. What else? Yeah.
I was wondering with the liquid model stars if singularities are at all possible, if that changes between like liquid and gas models, and then also if the two alternatives presented for black holes fit in with the liquid model.
Remind me what two alternatives did we talk about?
The alternatives were that they were supermassive star remnants or piles of cold dead stars.
Yeah. I think those are both congruent with the liquid model. So liquids, again, the simplistic view with liquids is that they're essentially incompressible. So the way that liquid stars even do fusion is not necessarily based on crunching stuff in the core the same way that it is in the gaseous star. There isn't so much, I don't want to say it's not gravitational, because that's not quite the right way of thinking about it. The idea is just that you don't need these excessive temperatures in the core to pull it off, because in the lattice-confined fusion experiments that we've done on Earth, there's something about restraining the atom's mobility in these layers of the lattice that does the work for you of holding them still. So you don't need these really high temperatures to do the fusion. And so, yeah. So, sorry, the first question was, do you get anything approaching a singularity? So no, absolutely not. The second question is, what's up with the alternatives in that case? Well, the alternatives, the sort of mundane alternatives with liquid stars is that they just sort of cool off and lose luminosity. And eventually, they're going to become these cold, I don't want to say dead, but cold, inactive, non-luminous objects, essentially. And I'm going to play with that a little bit more, because today we're going to look at the center of the galaxy with a little more detail. And there are actually some scientists, like we talked about the stellar remnants and so forth. And we're going to be talking a little bit about dark matter today, too, which is a similar problem where things seem to be there, but they're not. We can't see them. And the solution set is very similar under the liquid model, because, you kind of have to marry it to the work I was talking to you by Edward Dowdy about the bending of light in these plasma atmospheres of stars, right? So one of the principal arguments for why it couldn't be, that black holes couldn't just be cold, dead stuff, is that, and dark matter for that matter, especially at the center of the galaxy where we're expecting these supermassive black holes. One of the reasons for that is that these cold, dead things should be lensing due to gravity. There should be micro-lensing. In other words, when a star passes behind them, you should alter the position of that star just a little bit. However, if lensing isn't a gravitational phenomenon, and it's actually something more like a refractive mechanism or a diffractive mechanism, something about the edge of these objects going through some sort of either plasma atmosphere like we know exists on the sun, or if it's a diffractive element. And we haven't talked much about diffraction in this class, but we can play with that if you want. If there's some other process going on that isn't gravitational, then we shouldn't expect to see gravitational lensing of these things necessarily, especially if they're cold and dead and don't have that glowing plasma atmosphere anymore. That seems to be where we see the lensing, but in the case of our own sun, is right in that atmosphere, that corona area of the sun. So that's a good question. It's good to think about these possibilities. Certainly something interesting is happening there, and the center of the galaxies is a huge mystery, and we'll get into it in just a few minutes here, but something really interesting is happening. I mean, some galaxies have these enormously powerful jets shooting out of the center of them. It seems like, they're, at least in our own galaxy, it's extremely bright. You can actually see it in the night sky. You can look towards the center of the galaxy. It looks like a kind of ball at the end of the tail of the Milky Way if you go out at night on a good, clear night. There's something incredibly powerful happening at the center of galaxies. And yeah, it's kind of anybody's guess as to what that is, and especially if the black hole solution turns out to not be tenable going forward. What else, guys? Yes?
I find it interesting how they sort of talk about the selective bias. With certain black holes and things, like when we talked about the picture and how they have to edit it so much to make it fit.
Oh, that thing is a nightmare, yeah. What was the name of that? It was called like the Event Horizon Telescope too. Sorry, I'm just looking for your name on here. Yeah, I mean, selection bias is horrible. I was talking about that with my wife when I got home last night, or last class when I got home, and I was just talking about that situation, and I was like, you know, I think the reason that these people are willing to take one piece of data in a billion pieces of data, because it was 1 part per billion of actual pixelated data that they ended up using. So there were 6 voxels used to reconstruct that ring structure. And I was just talking to her, and I'm like, I don't know how people could actually do such terrible science. Like, it kind of blows my mind. And she was like, well, if you're 100% convinced that the only way to explain the galactic dynamics is a black hole at the center of them, and that's a completely foregone conclusion for you, and there's no space in your mind for that not even being a possibility, which is understandable, because if you end up being trained in astrophysics and you go through the whole pipeline, you do your PhD, you get a postdoc, you work at all these different telescopes, you reach a point perhaps where there's zero space in your mind that anything else could possibly be occurring. And therefore, no matter what you need to do to demonstrate that with your telescopes, you give yourself the authorization to do that, because you know for a fact that that's what's happening at the center, right? And so, I don't know, it's hard for me to put myself in the mindset of somebody doing that. But at the same time, you know, I think that all of us probably have things that we just take as bedrock reality. And if, you know, just things that we would never even question about our own lives, about the things that we go through. And if you just get used to that, maybe it's just a legitimate blind spot. And you kind of do whatever it takes to illustrate it. I have no idea. That's a crazy piece. I think it's, not only is it crazy, but I think it must be it's even too crazy to put in your textbook, which is really interesting. I totally expected to see that image in your textbook until I started looking at the data a little bit closer. And then I was like, you know what? I think even the authors of this textbook don't want the legacy of that being in there. Anyways, what else, folks? Thoughts about the, yeah, Kai?
I'm just looking at the text stuff
Yeah.
I'm wondering what makes a black hole rotating versus not rotating.
I think that's a great question. I'm gonna have to get back to you on that. I think it probably has to do with the amount, like the polarization of the X-ray emissions from the jets, right? So that's what's kind of interesting actually about those places. So whatever the heck is happening, let's just call this phenomena the black hole phenomena. So something is happening. There's something orbiting something we can't see. One of the interesting pieces of the puzzle is it does seem like there's these really strong X-ray and gamma ray signals, so really high energy light, basically, coming from these regions. Sometimes it's spinning. In the case of, sometimes the way that it fluctuates is interpreted as spinning. So in the case of neutron stars, they have these, they blink, and people interpreted that back in the 60s as these were neutron stars spinning. I think there's another alternative too, which has to do with this RC situation, which is very similar to the way that your turn signal is set up in your car, which is really just this relaxation oscillator whose ability to charge a capacitor and discharge it is, in some sense, primed by the circuit that's set up. So there's some possibilities there, and I think that the rotation is inferred by assuming that the blinking of that signal is due to rotation. So. Yeah, but I'll read up on it a little more and get back to you about that. But yeah, that was Roy Kerr's contribution as far as I know. I think Roger Penrose actually got the Nobel Prize a couple of years before that, if I'm not mistaken, for basically doing the math of how black holes would come to exist from a star, so the whole collapse business. And Penrose is still alive and kicking. Hello. Sorry. Former students. Yeah. What else? Yes.
You mentioned like galaxies are weird and that they appear to move all together, but not in a way that like a solar system would, orbiting each other. And so I was wondering if you could go into detail about what we know about our neighboring galaxies and how we're moving and how that relates on a much larger scale to what we're doing in the universe.
Yeah, that's perfect. We will do that today for sure. We'll look at the rotation curves and stuff. We'll get into it. Hold that thought. Anything else about black holes or singularities, data fabrication, over-biased interpretations of experiments? Yeah.
I found it interesting that the main difference between neutron stars and black holes, and that black holes have more mass than neutron stars.
Yep, and they're darker. Well, I guess they're both pretty dark. You can't really see a neutron star. Yeah, they're basically the same thing. It's just a matter of how much mass is inferred from the orbital dynamics. Very interesting. Yeah.
Do you think, like, part of the fascination, like, the theory of wormholes, because it's like a mechanism for us to, like, reach out further than it's physically possible?
100%.
Is that where the fascination comes from?
Yeah, 100%. I mean, so you have such a gentle voice, Michael. Yeah. Yeah, that's right. You were sick, but no. Michael's asking, back to the wormholes and so forth. Is this like, does it evidence this deeper desire we have to be able to reach into some other realm in some sense, or beyond what is physically possible, given this atomistic universe that we've inherited? And I think it absolutely does. I think all humans since all of time have been keenly aware that we live in a vastly mysterious universe, and there's things that happen to us in our daily lives most of what happens in our daily lives isn't in the physical domain. It's largely relational. It's largely, I hate to use the word spiritual, but it's largely spiritual. Like, we have relationships, we have love, we have friendship, we have enemies. We have so much going on that has, I want to say nothing to do with atoms, but let's say next to nothing to do with atoms. And so what's been really interesting in the last 300 years, really the last 100 years, since religion has become less and less of an appealing conduit to exploring those ideas for people, is that people have looked more and more to science to be able to explain these things. And I kind of take the position that that's a sort of unreasonable endeavor. Like, I don't think that science is the best way to explore a lot of those questions about reaching beyond physical reality and so forth. I think that's a great place for art, personally. I think it's great for myth, art. I think there's something real about it. I think myths often, I think art, stories, movies, even comedy, music, these are all great ways to explore what's beyond physical reality, but I'm not sure that physics, being the study of physical reality, can really even come close to touching those things. And what's worse is when we expect it to, it's going to give us back all sorts of nonsense as a result of it, because it's an unreasonable expectation. So it's kind of like, asking you to pick up a 1,000-pound weight, It's either going to break your back or you're going to fail to do it. It's just not a reasonable ask. So unfortunately, I think that's kind of what's playing out. But I think it's understandable in some sense. Oftentimes the way that everything unfolds here for people on Earth is this pendulum effect, where we got very, as a Western civilization, we became very dissatisfied with the church running the world back in medieval times. We swung really hard in the... Martin Luther, exactly.
92, was it 92?
I don't know. I couldn't tell you. We swung really hard in the other direction. There was this Enlightenment period. People really loved the industrial progress that resulted from scientific approaches to nature. And I think maybe in some sense we swung too far in the other direction at this point. But I'm not sure that religion is necessarily the solution itself either. I just don't know that we've come into a better way of approaching things. I mean, I'd love to hear what you guys think about this. For me, it's like since ever, basically every political structure, every state that's ever occurred on the planet has had some arm of moral imperative to it. It's always had some religious or spiritual imperative, right? Guided by some higher set of values. But what's really weird about the world we live in right now is that our political leaders are not at all beholden to anything higher than themselves. And I wonder if that's even tenable in the long run. Yeah.
It was
95 problems with the church.
Statements.
That Russian Roman Catholic Church.
Yep, there you go. Kicked it all off. But I mean, all of this observational science was happening at the same time. The world was just kind of ready for a sea change, it seems like. But yeah, I don't know. I mean, like maybe it isn't religion, but can we really get by forever without some sort of a moral compass that everybody at least upholds their leadership to or expects of their wider cultural, societal anchors? I don't know. What do you guys think? Is it possible? Does everybody, can we live in a world where people just kind of make up their own rules? Yes.
kind of already do.
Well, we're trying to. How's that going?
Well, sort of. It's like, if you really think about it, like in a philosophy kind of term, it's like, how do you know what's real? Is it what other people are telling you? Is it what you observe? How do we know what rules we should follow? Is this like personal? Is it just what everyone else tells you? Like, morals are a funky thing, because really
It's tricky.
it's up to you to decide.
I mean, it is until you violate something about my own sovereignty, right? Right. So so obviously laws are a great way to navigate most of that, right? But there's something about religion that I will give it credit for, which is that it's not simply about not violating your neighbors. It's actually a little more aspirational than that. It's like there's this mythological deity of some sort, whatever, and that's sort of the highest possible aim. And if we all sort of like recognize that and aim for it, none of us are going to be able to pull it off, but at least we have like some role model, some sort of like attempt at something that would take us beyond simply not violating each other. What do you think? The higher aim.
Because like it's misinterpreted or just interpreted differently depending on like the geographical location or how you're raised to interpret it. There are no singles.
Yeah, I mean that is the trick. It's like we live in such a varied world today. That could we even agree on what these like higher values are? I don't know. I don't know the answer to that. I also don't know if it's possible for us to sustain ourselves without them, right?
I feel like the golden rule is like the most solid.
I think most people would agree. Golden rule. But what about like the iron rule? My wife's always telling me about the iron rule. It's like or the platinum rule. It's like golden rule is like treat other people like you'd like to be treated. And I guess the iron rule is treat other people like they want to be treated, which is a lot harder to do actually.
And I guess it also depends on, does that person also follow the platinum rule, or are they just me?
Are they going to defect on you, right? Yeah. You guys heard of game theory? It's funny because mathematicians are trying to figure this out too. They're like, what's the ideal way to behave? Right? Of course, the scientists are trying to figure this out because the scientists are kind of the decision that, they kind of orient us towards the solutions in our modern culture. Game theory, anybody?
A YouTube channel?
No, game theory is this like highly complex mathematical modeling situation where you basically set up games, and they're not like silly games. It could be modeling how two countries are going to behave that are at odds over some natural resource or something. And the basic way that you can add certain weights to decision making in various cases, but the basic idea is, something like, will I betray you if I think that I can gain an advantage from it? And should I, if we have to, and the answer changes, should I betray you if I think I can gain an advantage and I think I can win this battle? Should I do it or shouldn't I? And the answer is kind of like, well, do you plan on ever playing with this person ever again? Like, do you plan on having to interact with this geopolitical neighbor ever again? And if so, then the answer is that generally speaking, you should allow people to betray you once, and then you should be open to playing another game with them. And if they do it again, then you don't play with them anymore. But the mathematical solution to this game theory essentially says that you shouldn't defect on people just because they defect on you the first time, which is really interesting. So yeah, people have tried to quantitatively solve this problem of morality, but it's not so clear necessarily. Plus, if any of you have ever been betrayed before, it's pretty hard to forgive people, even for doing it once. So that's a real nightmare. I don't know. Any thoughts? Yes, Diane. Oh, I'm sorry.
But I saw your video that was on future, and I thought it was interesting that there are places that bodies appear to be orbiting spots with no lights.
It is interesting.
So it's like we cannot see the black hole in our life, but we can know there is one because we can infer its existence by observing the motion of stars orbiting around it.
Yeah, that is exactly what the phenomenon is. Yeah, you guys know what do you guys know what a phenomenon is? I keep using that word. It's a real mouthful. It's also confusing because the plural of phenomenon is phenomena. But anyways, the phenomenon is just something that's apparent. It's like everybody sees something happening, and then the question becomes, for science or philosophy, what causes it? And what's interesting is that the phenomenon of black hole has been kind of mixed up with the explanation of black hole as collapsed space-time, singularity, rip in physics, whatever you want. There's certainly a phenomenon happening there. Something really interesting is happening at these points that we can't see. The question still in my mind, to be answered is what the heck is causing them, because I don't really feel comfortable with just throwing physics out the window. But yeah, that is a good point. Any more thoughts, folks, before we keep rolling here? Yes, one more.
It's a silly thought, but I have a theory about humanity that boils down to Star Wars or Star Trek.
Okay.
Which one you're more agreeable with
Oh, interesting.
your outlook on humanity.
Okay.
So, do you like Star Wars or Star Trek better?
I mean, I didn't really grow up with Star Trek, but my wife has showed me a few episodes, and I get it. But I'm definitely lean towards the Star Wars side of things.
My theory is that people who tend toward Star Wars
Yeah.
also tend to view humanity a little more pessimistically because it makes sense, and that people who tend toward Star Trek tend to believe that humans can kind of overcome and get to a place where we can work cohesively, so let's fulfill our nature to be adventurers.
I mean, even the name, right? War versus Trek. It's like, which one do you align with? I don't know. I feel like I've opened myself up to both sides at this point. I don't know. The universe is insane. Like, living in this world, being alive is insane. There's every degree of tragedy is occurring right alongside every degree of just unimaginable wonder and magnificence. It's almost too much to handle sometimes. But yeah, those are definitely two modern mythos of the future. So Star Trek, of course, is right where these explorers going around and inventorying other worlds, and I think they have a basic ethos of not doing harm and so forth, right? And Star Wars is more like the evil overlords have taken over, and we have to push them out of the way.
There's a third lesser option, which is Farscape.
Oh, I don't know that. Yeah.
But it basically boils down to it doesn't matter if you believe optimism or pessimism, and people just sleep with each other, war, have friendships, and fuck each other up all the time anyway. So
Yeah, it's tricky. It's tricky. Plus, I mean, the whole thing is a big experiment. I think it's worth, I'm pretty optimistic, but it's worth noting that, almost every species that's ever existed on the planet is gone. So all of these experiments play out. Obviously, each one of our individual lives will be gone at some point pretty soon, depending on how you count. And, there's a transientness to all of this. And I would personally, I don't know how you guys feel, but I'd like to think that there's lots of Earth-like places out there doing their experiments, and probably some of them are working out better than others, and we're kind of one of those experiments that's going on. I think that incredible transformations are possible. One of the things I'm always playing with is, what does it look like for a civilization to persist for more than a few hundred years? Because most of them don't. If we look at the history of civilizations, incredibly powerful civilizations, maybe the winners, the max longevity ones go for 1,000 years, right? Most of them go for a few hundred years. And we're kind of at that few hundred year place right now. And it's, and you talk to people, one of my friends runs he's run a bunch of huge mega companies. And he has this thesis of basically how institutions have a lifespan. They're just like humans, basically. They're startups, they're babies, they get going, they essentially grow to some point, and then their innovative capacity falls off once they get too big. They get too cautious, and they basically stop being able to make new kind of like Apple, honestly, is a good example, right? They had this brilliant idea, right, at some points, amongst other ideas, but nowadays it's just what are they on, iPhone 35 or something? I have no idea, right? They just keep doing the same stuff. 17, okay. So these companies just kind of just age, and they just eventually just kind of can't do anything new, and they get replaced by other companies, and they just die. And so he has this really pessimistic outlook on the future of civilization, because he's look, this is just the way it goes. These things get too big, they stop being able to adapt to new circumstances, and they die. And that does seem to be historically true. But I wonder if it has to be true. I wonder if, on some other experiment somewhere, or even in our own experiments with this democratic republic thing that we got going on we call the United States. Like, can we invent a new version of ourselves? Can we reboot Apple, basically, right? Can we actually invent something new? Can we find a way to push through that? I mean, I like to think that it's possible, at least. I'm not sure what the roadmap to that exactly looks like. But yeah, history would say that you either do something completely revolutionary and radical, or you suffer the institutional fate that everybody else has suffered since ever, basically. I don't know. Any more thoughts? Yeah, hit me.
Before we do totally off,
Yes,
since you brought it up,
yes.
what were your thoughts on Interstellar when you watched it?
I mean, I can suspend my disbelief for science fiction for sure. I loved it. Yeah. I mean, I saw it like 10 years ago or something, but
I just thought it was like conceptually really good.
yeah,
Because it made people think about things they hadn't thought of.
100%.
You know, like,
I love science fiction. Like, I love science fiction. It's my favorite kind of movies and stuff, for sure. But and you know, I think actual, like, real good comes from imagining futures, too, in different ways as well, right? I loved, anybody see The Expanse? I thought that was a really good one. Nobody saw it? It's really good because it kind of plays out what I think is really going to happen very soon, which is we're going to start colonizing this solar system. The asteroid mining is proving to look really lucrative. I mean, there's like global GDP's worth of rare earth minerals in some of these satellites, or these asteroids. Anyways, it plays out, the movie, or it's like a TV show, I guess. I think it was an HBO series. It plays out kind of like what would happen when people start, what's going to happen when people start branching out and doing all this asteroid mining, and you know, how do we avoid all the like colonial pitfalls that we've kind of been through in the past, and what does it look like to have people living on Mars where you have to live underground, right? Because the radiation's so bad, and who are going to be the types of people that end up getting into those things, and what will become of Earth? And these are like really good, real questions that we should be kind of contemplating before we're actually out there doing it, you know? It's like, if you look at historically what's happened, it's often, you know, if you think about the people that were sent from Europe to come and pioneer the West in some sense, you know, the New World as it was called, they're pretty gnarly people for the most part, really tough. They were running away from persecution often back in Europe. So, you know, you could see similar things happening in the future, and you could see the old world becoming a very difficult place for people who didn't have that, let's say, kind of old money to really remain in. Like, it could become an unaffordable place on Earth if we're not careful. There's a lot of really interesting ethical questions. So anyways, I think science fiction is a great place to explore all that stuff. And the cool thing is you can just break rules of physics in science fiction, and it doesn't matter because it's going to serve to move the plot forward so you can think about the bigger questions that underpin the plot line itself. So.
I was in with the physics of Interstellar until they went in, but came out.
How do you do that? Yeah, you got to just suspend your disbelief. Yeah, I mean, I often get accused of being a materialist because I'm always insisting that physics has to remain material, but that's not because I think that material explanations for nature are the most powerful ones. It's just, what the heck is physics if it's not material explanations for phenomena? It's like, it's not supposed to explain everything. Like, I just want to shake people sometimes. It's not the whole story. Physics is half of the universe. There's something crazier going on in this classroom besides atoms, I'll tell you that for sure. And what that is it's a different class, I guess. All right, let's keep this train rolling a little bit. This should be a pretty mellow lecture compared to the previous ones. I want to talk to you guys a little bit about the history of the observations of the Milky Way so we can get caught up on that. A little bit about the structure and we'll eventually get into formation models, probably not till next time. And then of course, dark matter is the kind of missing piece of this whole puzzle. You know, people have actually, so have you guys all seen the Milky Way at night before? You gone out? Pretty obvious, right? On a really, especially down here in Oregon, in Southern Oregon. Really nice, beautiful just Milky Way, right? It looks like a big white cloud kind of stretching across the sky. It's kind of sad because if you live in a city, you never get to see that. But anyways, our ancestors saw it, and they noticed it for thousands and thousands of years. So if we go all the way back to, say, our oldest Western ancestors in terms of actual writing and so forth, we get back to the Babylonians, and they knew about it too. Oh, they didn't know that it was, this cloud that contained billions, hundreds of billions of stars. They actually talked about it as this slain serpent in the sky, which, the Babylonian creation myth actually involves the slaying of this serpent named Tiamat, where the leader Marduk slays this giant serpent. And what's really interesting, I mentioned this ties into what we were talking about earlier, but what's really interesting about the Babylonians is that they named all of their kings after this slayer of Tiamat, this hero named Marduk. So if you were going to be a king of the Babylonians, they would call you Marduk whatever. They'd give you a last name too. But the idea, and this is kind of true in Egypt too, was that the king should be deified in some sense, in that we hold the king to the highest possible value structure that we have as a culture. The king, and if the king stops behaving like a Marduk, then we cut his head off and get a new Marduk, basically, which is a really interesting framework for everything. So, anyways, they sort of set their civilization, they set their cosmology is set in amongst this slain body of this serpent. And a lot of you maybe weren't here, but we did a lecture on mythology, and we talked a bit about these serpent myths and how they kind of sprawl forth from almost every corner of the culture. And that's a really interesting thing. If we go all the way back, the oldest site in the West is called Göbekli Tepe. It's in Turkey. And there's all of these serpent motifs that are found on the carvings there, right? The serpent is one of the oldest images that we find, and many, many indigenous cultures refer to the galaxy as this serpent. Like I said, you can see the center bulge at the center of the Milky Way, and it kind of looks like the head of a serpent, so there's been some people who have interpreted it that way. At any rate, the Babylonians set themselves kind of amidst this slain dragon, which is interesting in the context of the mythology, especially, if you kind of see humans as the ones who sort of tame nature, it kind of starts to make a bit of sense. All right. So, where else? It's interesting. Over in the Andes, the Peruvian indigenous people actually talk about the shadows and not the actual bright spots. So they see different animals in the shadows between the spots between the big column of stars on the Milky Way. At any rate, the material story of the cosmos picks up for the first time, as far as we can tell. Big surprise in ancient Greece, right? So we had Anaxagoras and Democritus, who were these preeminent philosophers who actually both proposed independently that the Milky Way was the glow of stars. And so that's a really interesting moment. It's kind of the first place this happens. It's about 300 to 500 BC. Those guys were actually considered like extreme rebels in their day, which is kind of funny. By the way, we don't have their original writings. They've just been inherited down orally and then translated by the later classic Greeks and the Romans after them. But yeah, it's kind of funny to think about these guys giving material explanations as being absolute rebels. So eventually, actually, in classical Greece, people didn't entirely buy this, and Aristotle ends up saying he thinks that it's actually an illusion caused by something in our own atmosphere as we're looking up at the sky at night. So this idea that it's a bunch of stars kind of gets lost. I don't know if you guys have thought much about ancient Greece. It's kind of an interesting situation. It was like not so much a single country, but it's all these different islands, right? And every island kind of had its own, the first version of anything approximating what you guys are at this university today. They had these things called academies. And the academies would have these different resident philosophers. And so each island kind of had its own approach to understanding things. And of course they would talk to each other. But they're separated by sometimes, hundreds of miles and stuff. So people would really develop completely different approaches to understanding reality. And then we, of course, only inherit a few of them when we think about the ancient Greeks, but there was like hundreds of these. It's almost hard to imagine. It's like the closest thing to this modern university system of all these different universities that we have today. It's pretty crazy stuff. All right, so yeah, so Aristotle, he's like, I think this is something in the atmosphere. Not everybody's buying it. So we skip forward, hundreds of years. We get back to people resurrecting the idea that it's actually stars. So the first person to do that was actually a Persian astronomer named Al-Biruni, who proposed, quote, that the Milky Way was a collection of countless fragments of the nature of nebulous stars. So he basically was like, look, these are all little baby stars, which is totally reasonable proposition. Later on, keep moving down through the history. Another Persian astronomer proposes that it is actually individual full-on stars. This is Nasir al-Din al-Tusi in 1201. Actually, that's when he was born. But between 1201 and 1274 proposes that these are tightly clustered stars. They seem to be cloudy patches, but they also adopt this idea of the Milky Way as a result of this. So the first time that anybody actually had any physical evidence of this being the case was when Galileo pointed that looking scope up at the sky. And that was the first time that anybody could actually resolve individual points of light as being part of this milky structure in the sky that people had been watching for thousands of years. So, it's kind of funny because Galileo also he did note these pointillated pieces, but he actually assumed that it was an atmospheric refraction thing himself at first. And it actually he made drawings of it and so forth, but it actually was several, 150 more years before the same philosophers, Kant and Laplace, the same people who gave us this rotating formation story for our solar system, really started to play with the dynamics of what it would look like to have these individual points of light be stars, and if that would even make sense. Was there something similar to what held our solar system together, right? Because the solar system was a new idea all of a sudden. Was there something like that that could be holding all these stars together? Basically a precursor to gravity. It's kind of ironic that Kant would be proposing these kinds of things. Do you guys know anything about Kant? Have you guys had to read Kant in any of your classes? What do you guys read in college these days? You guys don't have to.
Theory of computation.
Oh my God. All right, you should read some, you need to read some of these philosophers. So Kant's kind of funny. I'm not a big fan of Kant, but you should read him. Because Kant had this idea that the world is kind of, that everything's sort of happening in your head, and that, in some sense it's a little bit pointless to try to figure out how the universe works, because at the end of the day, the only thing you can trust is what's going on inside of you. Which is kind of a fair point. I mean, everything that you know is definitely happening inside of you, right? You have a brain, and presumably, and your brain's putting together all these things. Like, I can kind of see where he's coming from, but I'm not sure that it's a very practical philosophy at the end of the day. Anyways, I just think it's interesting because Kant's idea that the world is unknowable is ironic, considering that he was one of the first people to deduce the formation of galaxies, Milky Ways, and the rest. All right, so Kant puts this forward. In 1785, this dude we've talked about before, William Herschel, actually starts counting and laying out a picture of what these stars look like that would trace out the Milky Way. So he's kind of trying to reconstruct what this big sea of stars around us would be shaped like for the first time. Now Herschel, I love this guy because if you'll recall, Herschel was also the dude who noted that the sunspots appeared to be cooler than the rest of the sun. And he thought, my goodness, it must be really nice inside of the sun. I bet there's people living inside the sun. So he came up with this idea of the Solarians, which I think is not only super fun, but it's also extraordinary because he wrote about the Solarians haphazardly, sort of just as like a cast-off sentence in a very serious publication about the material basis of the sun in the Annals of the Royal Society. So it was just such a very different time back. This is, 200 years ago or something, when people were so much less touchy about what they could write about in their scientific journals. It's kind of unimaginable. Anyways, all right. So meanwhile, maybe let's skip forward another 100 years to like mid-1800s. People are starting to try to resolve with telescopes the fine structure of these other things that they saw in the sky, which they called spiral nebulae. So they saw these other cloudy things that were kind of spiraling. They thought maybe these are solar systems forming, something weird's going on. They start to actually note different structures of them. So they note there's elliptical ones. They note that there's spiral-shaped ones. But there's more detail to these nebulae than people had ever thought before. What else? So people were also starting to take note of the fact that these nebulae were really, really faint sometimes. They had detail, but their magnitude of brightness was really, really, really faint, like 10 times weaker than, say, the normal stars as part of the Milky Way. And they started to think that that was kind of interesting. And you start to see the first time that people are proposing, wait a second, what if they're just really far away universes, kind of like our little universe, but they're really far away instead? So they started calling them island universes for the first time. So this was 1917. But people were like, could something really be that far away? It's kind of unimaginable. The distances required to have a cluster of stars just as big as ours that was that far away that it would be that dim was kind of unimaginable to people. The distances were just absurd. Something like 150,000 parsecs away. So, millions, if not hundreds of millions of light years away. Okay. So people kept fighting about this. If we fast forward, there was a huge debate about distances, but it was still people kind of splitting hairs over things that they couldn't directly observe. It really, and by the way, this is a good picture of the Milky Way, which has all of these little satellite nebula around it. We now think of them as satellite galaxies, but they're basically little tiny ones that are near us. And then there's also actual entire galaxies which are further away, and people were trying to discern the difference between these little ones and these big ones. So there's a couple of little local little galaxy-lets all around us, which is quite interesting. And then there's these other ones, and people were trying to resolve the differences between them. And it actually wasn't until the 1920s when Edwin Hubble was able to actually get a really good method through the Cepheid method that we talked about of distinguishing distances between stars, that he was actually able to make the claim that that Andromeda galaxy over there was indeed as far away as it would be in order to be a completely separate and fully fledged galaxy. So that was the first moment in 1920 when people really accepted, by and large, the idea that our galaxy was not the universe, which is super far out if you think about it. So it's been 105 years that the galaxy hasn't been the entire universe. I mean, you got to let that sink in for a second. All right, so let's look at this thing. This is our map of our own galaxy. Now, of course, we can't actually look at our own galaxy, but what we can do is, at this point, and over the last 100 years, we've been able to resolve a lot of other different types of a lot of other galaxies. And what we can do is we can look into the region around ourselves and start to construct density maps, right? Kind of the way that you would do an image of like a person, like if you go to the doctor and get a CT scan or something like that, they can do these slices of you, right? Can kind of do the same density reconstruction, and then we compare it against galactic structures that we can see in other galaxies, and we essentially glue that all together and say, well, we must have this kind of galaxy because that map fits the best. And this is more or less the structure that we end up with. Now, what's kind of interesting is that although the galaxy looks like it's kind of this pinwheel structure, so it has these arms to it, and it is true that we actually are living inside of one of these arms right now. The region in between the arms is actually really dense too. It's full of neutral hydrogen and things that don't actually make nice bright light for us. It's not necessarily full of stars in the same way. So the galaxy is actually pretty hefty through and through. It just has this optical effect of looking like a pinwheel at the end of the day. So, it's probably been 50 years only since we've had this idea that our galaxy is one of these nice spiral structures. And we're still kind of piecing together the structure, especially as we begin to understand these gaseous components. They can give us a sense of what's going on here. So our sun is on the inner edge of one of the shorter arms here, which is called the Orion spur, which, let's see if we can see this in here. Yeah. So this is the Orion arm. Oh, no, it's not. There's the Orion arm. It's kind of in between the two big ones there. And that's where we are hanging out today for this lecture. Oh, there's a better, closer picture of it. The Orion spur. It's kind of a little armlet in between the two big arms. Now, what's kind of really perplexing about all of this, too, is that our sun is making its way around the center of the galaxy. It takes, I want to say, around the order of 250 million years to do this, to do an entire revolution of the galaxy. But it doesn't just stay in the arm when it goes around the galaxy. It actually moves through the different arms of the galaxy as it goes around it. So the individual stars actually process kind of independently through these arms, but the arms still retain their structure as it happens, presumably. So this is quite fascinating, which has incredible implications for the history of our solar system and our Earth, because you got to think, there's times when we go through these really sparse regions, right? In 250 million years, that's not that long, right? If we assume that, the planet, the history of the planet, at least we can assume life goes back maybe 3 billion years, which is like 3,000 million years, right? So every 250 million of those, right, we're making our way all the way around the galaxy. That means that we go through regions that have almost no stars sometimes. But other times, we're inside of these really densely packed arms where there's lots of stars, which means probably lots of interactions too, whether it's cosmic rays, whether it's supernova, whether it's just chance gravitational interactions with other stars. So there's all these different moments in this long, long year, whatever you want to call it, really, really long period of this cycle that our solar system goes through. Kind of fascinating. So a little bit more about the structure of this thing. There's a sort of a main disk to it, a plane in which, let's say, most of the dense bodies are found, most of the stars. We also have this kind of halo of material around it, which contains all these tiny little clusters and globules that seem to have kind of drifted out of the center line. Now, the ones that have drifted out, people think they're much older. That generally comes down to arguments about the elements that they contain. So if you guys think back, the argument is given that our star, I'm not sure I agree with this, but the argument is given that our star is a second or third generation star because it contains elements that it couldn't possibly have fused itself. So it must be made out of the leftover recycled remains of much bigger stars that fused all those elements. But these populations that are outside of the main disk, they seem to be oftentimes old and kind of enriched in all those elements as well. So that's kind of interesting. What else do we want to say about this? All right, so yeah, this disk kind of extends out to 150 light years from the center. It's just it's an enormous structure. It's very difficult to comprehend. So one thing that's kind of interesting is that, in terms of the way that this thing rotates, I mentioned to you that our star does move through the different arms. This is true. And in some sense, the galaxy does move like a solar system. So stuff that's closer in to the center does go around faster than stuff that's at the exterior. That kind of gives it this spiral-like structure, I suppose. but it doesn't do it exactly like a solar system. And that's kind of the heart of the problem in astrophysics right now. It's kind of one of the biggest issues on the table, aside from the Big Bang, which we'll eventually work towards. And it is this: why is it that the stars rotate around the center, much like our solar system? They rotate faster in the interior and slower in the exterior, but not exactly like our solar system. In other words, there's a bit of homogeneity to it. There's a bit of the thing rotating as a consolidated whole on an order that solar systems themselves don't seem to do. So this is called the galactic rotation problem. And it's actually a bigger problem than you would think, because there's only a couple of ways to solve this problem. One is that gravity, as we understand it, this nice inverse square law that we talked about at the beginning of the course, that it kind of stops working at some point. Like, gravity falls off with an inverse square, except on extraordinary distances. And on those distances, maybe it falls off something less than an inverse square. So there's maybe a little more gravity than we thought there should be on huge space length scales. The other possibility is that there's something really heavy out in the outer arms of the galaxy. And that heavy weight is kind of dragging everything at a homogeneous speed with it. So in other words, this is what we actually have over here. You can look at the speed curve versus distance from the center. And it's, here's maybe a better view of that. The red curve is what we actually observe. The blue curve is what's predicted based on the luminous matter that we can see. So if we just add up all the stars and their weights and from their gravitational interactions, we add up their weight, it seems like they should be moving slower than they are, but they're moving really fast, faster than they should be moving. So it's really interesting. So the only other possibility is that there's stuff out there in the outer arms of the galaxy that's heavy and we can't see it. What does that sound like? We've heard something like that before in this class, right? So, again, we have a phenomenon, which is stuff is moving like there's something there, but we can't see anything there, right? So this stuff, this phenomenon gets reified, it gets converted, concretized into an actual thing. Right? Just like black holes are also a kind of phenomenon that is something moving around something we can't see, some sort of strange X-ray signals coming from some location. We can't see it glowing. And so turn it into this object over time called a black hole. We turn this phenomena into another set of objects, which is called dark matter. So, there's a great deal of effort going on to try to find a solution to this problem, which is based on detecting something that we've never experienced or encountered on Earth before, something really heavy that doesn't emit light. And people are thinking, well, maybe it's a new type of subatomic particle, something extraordinary, some sort of unimagined substance that perhaps we'll be able to see at some telescope here on Earth if we just build the right telescope. And it might be so. That may be the case. I don't really have any reason to believe that it's not the case, but I do think there's probably more mundane solutions to it, like we were talking about with Rook at the beginning of class. It's certainly conceivable following a liquid model, especially married to an extended timeline for the universe, that you would have a lot of cold, dead stuff lying around. And so that's actually been entertained. So let's work towards that in the last few minutes here. So, the argument is given that it can't be elemental gas. If it was neutral hydrogen, we'd get that 21 centimeter line from the stuff that's out there. It can't be ionized hydrogen because it would be emitting visible radiation. It can't even be a bunch of black holes because then we should see a bunch of X-rays coming from it. We don't see that. So, what's happening? And I've gone over one of the possibilities for you already. There's a possibility on the table that obviously it's an exotic form of matter we haven't studied. That's dark matter. There's also a group of physicists that have some traction right now who are arguing for modifying Newtonian gravity. They say, hey, we actually have to change Einstein's equations, we have to change Newton's equations because they're just not applicable at these great length scales. That's called MOND, for modified Newtonian dynamics. There's also the problem of just there's the possibility of mundane cold ordinary matter. And so it's interesting because there are actual astrophysicists arguing for this right now. I found this line in your textbook that said brown dwarfs and lone Jupiter-like planets have been ruled out. Well, they haven't really exactly been ruled out. So the argument against those is, generally speaking, that there's a couple of arguments, but the strongest argument, let's say, is that they don't seem to do any there's no gravitational lensing of light through these regions. And that if there was huge weights of dead planets out there, or dead stars out there, they should be lensing the light. And again, I would have to bring us back to the Dowdy argument that the sun doesn't appear to be gravitationally lensing light so much as something else is happening in its plasmatic atmosphere. So what do they call those things? They call them Rambos, actually, which is a pretty funny name, which stands for Robust Association of Massive Baryonic Objects. So basically, old dead stuff could be out there doing it as well. That was a very thoroughly entertained idea back in the late 90s, but again, all this gravitational lensing stuff has led to, let's say, a loss of interest in it in the mainstream. I also had a really interesting conversation as another possibility. So I don't know, I think we talked about it last semester, but we have there's something kind of interesting happening. Our sun is spraying like a fire hose in all directions, but particularly it's spraying out all of this hydrogen all the time, right? It's called the solar wind. It's just really fast moving, almost relativistic speeds, like fractions of the speed of light, really fast moving atoms just flying out of this thing, ionized atoms. And what happens is when all of that solar wind hits the interstellar medium in front of it, it forms this kind of shock wave structure. And the result is that each solar system is kind of a little bubble. As it's moving through the galaxy, it's kind of crashing into the interstellar medium, and it forms this little shell around it, which is called the heliosheath. And it has this long kind of cometary tail out behind it, because it's not encountering as much resistance in the rear. And so you have these kind of droplets. Each one of these stars are making droplets. And I was talking to this gentleman named Eric Sternstein at some point. He's an astrophysicist at Princeton, and he studies the heliosheath. And I was playing with this idea with him that there might be some sort of really interesting hydrodynamic effects that happen such that these different bubbles could in some sense intertwine with one another, and that could have some cohesive effects to it. So there might be, in other words, there might be some sort of velcroing between these different helios sheets in between the different stars, right? So in between the solar systems, they might be somehow velcroed to one another because they have these bubble-like structures that surround them. And in effect, you might get some ability for the stars to link up to one another that wasn't purely gravitational as a result of it. So half-baked idea, but an interesting possibility nonetheless. There's so few people studying alternative approaches like this that I imagine the story that whoever's teaching this class 100 years from now will be very different than the one that we have available to us today. So last 5 minutes, we've kind of reached the center of the galaxy. And the center of the galaxy is kind of extraordinary. It's, like I say, a really, really, really bright, dense region with gazillions of stars in it. And, you know, in order to essentially hold the whole thing together, astronomers have posited that there's a great deal of missing mass, once again, at the center of the galaxy. So again, we have another phenomena. Stuff is pulling on these stars. Their orbits don't make sense, and there's something dark that's doing it that we can't account for. So we plop an enormous black hole at the center of this galaxy. It's called Sagittarius A, which is in the direction of the constellation Sagittarius. This is kind of the state of the art of the situation. Now, there's problems with the black hole argument with Sagittarius A, namely the one that Dowdy points out, which is that we don't actually see any of that lensing stuff with respect to the starlight coming from the center of the galaxy, which is kind of a nightmare as well, because if you have this supermassive object, again, if gravity is actually lensing light, not sure that it is, but if it is, then why don't we see lensing events coming from it as well? And as you can imagine, the alternative solutions besides a supermassive black hole at the center of the galaxy are very similar to the solutions that we've proposed as alternatives to the outer limbs of the galaxy, so cold, dead stuff, more mundane processes. But something really incredible is happening, and there's a giant X-ray source there, and it's a huge mystery, to be honest with you. So there's lots of, there's lots of genealogical problems with what's happening there. There's really old, cold red stars at the center of the galaxy, right next to really bright, young, fresh, hot, super bright blue stars. It's a very interesting hodgepodge of appearances that don't necessarily have any obvious story to tie them all together. So I think where we'll go from here is we will start looking at all the other galaxies with respect to ours, and we'll start tying them into a general picture of how they're all moving with respect to one another, which will get us one step closer to a cosmology, at least a physical cosmology. I can't give you guys a spiritual cosmology, unfortunately. But we did it again, guys. Congratulations. And have a good week. I guess, what is it, Thursday? Have a good weekend, and I'll see you guys on Tuesday.